I'm Fleshed Out Thoughts, and I'm building a full-stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I do differently. Today we're going to be getting into estimation and capacity planning, how I size systems from my e-commerce platform to Twitter scale. Do I need a read replica? How much storage will I need in 5 years? Will my database handle the traffic from a product launch? These are infrastructure questions, but before they're infrastructure questions, they're math questions. And the math is fast if you know the right constants. Back of envelope estimation is a reasoning tool, not a prediction tool. The goal is to identify which resource will hit its ceiling first, the binding constraint, so you can fix it cheaply before it becomes a production incident. At my current scale of less than 1,000 daily active users, the binding constraint is connection management, not reads, not writes, not storage, connections. That's why PG Bouncer is in place and a read replica is not. This video is about how to do that reasoning. The numbers worth memorizing, the math for converting user count to infrastructure requirements, and the specific capacity numbers for my platform today. Why estimation? Identifying the binding constraint. 3 estimation questions with their full working. Do I need a read replica? Less than 1,000 daily active users, 50 requests per session, 50,000 reads per day. 50,000 divided by the 86,400 seconds per day is roughly 0.58 reads per second. Postgres handles 10,000 or more simple reads per second on a single node. At 0.58 reads per second, I'd need to grow by 17,000 times before read throughput becomes a concern. The answer is no, not for years. Will I exhaust Postgres connections? Versailles scales to n function instances. Each instance opens one connection. Default max connections is 100. At 100 concurrent requests, a moderate traffic spike, connection exhaustion occurs. Without pooling, this is the binding constraint. The answer is yes. This needs to be solved before significant traffic arrives. How much storage for 5 years of order? 1,000 orders per month times 60 months is 60,000 orders. An order row is approximately 1 kilobyte. Order items at 3 per order average. That's 300 bytes. Total, roughly 1.1 megabytes for 5 years of orders. Orders is not a storage concern. So the answer, it's negligible. Blog content and product image are what drive storage. These 3 calculations take 60 seconds. The answers are directly clear for the architecture. Invest in connection pooling. Don't invest in a read replica. The numbers to memorize. 2 groups of constants, latency and throughput, that make envelope math fast. Latency L1 cache reference is 0.1 milliseconds. That's in-process memory access. Database reads from shared buffers when the page is hot is also roughly 0.1 milliseconds. SSD random read is around 1 millisecond. HDD mechanical seek is around 10 milliseconds. Avoid in any hot path if possible. Same region network round trip is around 10 milliseconds. Cross region is around 100 milliseconds. A Stripe API call is around 200 milliseconds, so the throughput at scale, 86,400 seconds in a day. Divide and daily count by this to get per second rate. Postgres handles 10,000 simple reads per second on a single node. Write transactions, 2,000 to 5,000 per second before contention. Default max connections is 100. Memory cost per connection is approximately 5 megabytes. The typical order row size is approximately 1 kilobyte. Postgres page size is 4 kilobytes, the smallest unit of I/O. These numbers let you do envelope math without looking anything up. Is 200 milliseconds for a Stripe call a concern in a 2-second SLO? 200 milliseconds divided by 2,000 milliseconds is 10% of the budget. Worth noting, but not a blocker, is 0.58 reads per second a concern for a 10,000 read per second database? Probably not for years, right? Request envelope math, DAU to QPS. The QPS gauge shows where my platform sits on the scaling ladder, well below 1 QPS average. In the far left of the hobby project zone, with the startup scale threshold of 1K QPS roughly 3,000 times away. The worked example. 3 assumptions produce a concrete infrastructure check. Assumption being 1,000 daily active users. The peak hour is 10x the average. Average session is 20 page loads and 5 API calls. 25 requests per session. For daily totals, 1,000 times 25 is 25,000 requests per day. 25,000 divided by 86,400 equates to 0.29 requests per second average. The peak, 0.29 times 10 equals 10.9 requests per second. The infrastructure check, Vercel handles 1,000 requests per second. I have 333 times headroom. Postgres handles 10,000 reads per second. I have a 20,000 times headroom. The connections, 3 requests a second times the average 50 milliseconds request duration means approximately 0.15 concurrent connections in flight at peak. 100 max connections means I have 666 times headroom on connections too. At 1000 DAU, nothing is anywhere near its ceiling. The binding constraint at this scale is not throughput, it's the cold start connection problem that pooling solves. Storage estimation. The storage SVG shows the breakdown across all data types. Row level storage is tiny. Binary files are what matter. The orders table. 1,000 orders per month, 60 months, around 1 kilobyte per row, 60 megabytes for 5 years is pretty negligible. Okay. Order items, 3 items per order, average around 300 bytes each. That's 54 megabytes for 5 years. Again, pretty negligible. The blog content in JSON-B, 50 posts, average 20 kilobytes each. That's 1 megabyte. Tiny product images, 100 products, 3 variants per products, 500 kilobytes per image. That's 150 megabytes. This goes in Supabase storage, served from a CDN. User profile photos. 10,000 users, 200 kilobyte average. That's 2 gigabytes. Supabase storage, CDN. Application logs, 100 kilobytes per hour, 8,760 hours per year, 2 years. That's 1.7 gigabytes, but the 90-day retention policy limits accumulation to about 700 megabytes at any point. So the architectural conclusion, store all binary assets in Supabase storage. The database holds only structured data. CDN serves assets to the users. The database will never be a storage concern at this scale. The Supabase Pros plan is 8 gigabyte limit, and it won't be approached by row data. Traffic patterns, peak versus average. Average QPS is not the design constraint. Peak QPS is. The ratio between them determines how much headroom you need. The 10x rule. For typical consumer e-commerce, peak hour traffic is roughly 10x average daily traffic. At 1,000 DAU, that's 2.9 requests per second peak. At 100,000 DAU, it's 290 requests a second peak. For e-commerce specifically, launch day and sale day can be 50 to 100 times average. A significant press mention can produce a similar spike. This is why the database must have headroom and why connection pooling is so important. Vercel scales the HTTP layer automatically, but the database can't elastically scale in seconds. There are 4 traffic shapes worth understanding, in my opinion. Dineural, most e-commerce peaks between 7 p.m. and 10 p.m. local time. ISR handles the page traffic. The database load stays flat and they're event-driven. Product launch or sales announcement. The spike hits the checkout specifically. Connection pooling absorbs it. Crawler traffic. Bots crawl all pages systematically. But ISR means they hit the CDN edge, not the origin. Geographic concentration. If all users are in one time zone, the peak to average ratio is higher than a global user base. My platform. Capacity numbers today. 7 resources, current utilization, ceiling value, and headroom. HTTP requests, around 3 requests a second peak versus 1,000 requests a second ceiling. 333 times the headroom. It's not a concern. DB reads per second, around 0.5 reads a second versus 10,000 reads a second ceiling. That's 20,000 times the headroom. Not a concern for years. DB connections, around 2 concurrent versus 100 max connections. That's 50 times the headroom. But pooling is already in place, so this won't become a concern even as traffic grows significantly. Database writes per second, around 0.02 writes a second for checkouts versus around 2,000 writes a second ceiling. That's a 100,000 times headroom. That's not a concern. Okay. The storage DB, around 50 megabytes versus 8 gigabytes. That's 160 times the headroom. The storage files, around 200 megabytes versus 100 gigabytes. That's 500 times the headroom. Stripe API rate around 0.001 requests a second versus 100 requests a second ceiling. That's 100 times the headroom. The conclusion is clear. 1,000 DAU, I'm nowhere near any ceiling. The only constraint that required attention was connections, and PG Bouncer is in place. Read replicas, vertical scaling, and partitioning are all at least a year of growth away. Latency budget, decomposing a 2-second SLO. My checkout SLO is 2 seconds. The budget breakdown shows where that 2 seconds was. Zod validation, the first millisecond budget, around 0.5 milliseconds actually. Auth verification, 5 millisecond budget, around 3 milliseconds actually. DB read cart and validate coupons, a 10 millisecond budget, around 5 milliseconds actually. DB lock and check inventory, 15 millisecond budget, around 8 milliseconds actually. Stripe create payment intent, 300 millisecond budget, around 200 milliseconds actually. And watch this one. DB insert order and outbox transaction, 20 millisecond budget, around 12 milliseconds actually. Vercel Edge network, 50 millisecond budget, around 30 milliseconds actually. The total, around 400 millisecond budget, but actually around 260 milliseconds. 4 observations to pay attention to. The Stripe is 77% of the total budget at 200 milliseconds. This is why all post-purchase operations, email, license generation, etc., are in the outbox and not in the checkout transaction. DB operations are fast at 12 milliseconds for the full order transaction. Even at 10 times the load, they'd stay under 50 milliseconds. The SLO has 87% headroom, 260 milliseconds actual versus 2,000 milliseconds SLO. Stripe would have to degrade 7 times before it breached. Where to optimize if needed? Pre-validate the cart before calling Stripe so the Stripe call only happens when the cart is known to be valid. Estimation in practice. The 60-second drill. Any infrastructure size in question is answerable in 60 seconds with 4 steps. Step 1. Establish the load. How many DAU? What's the request mix? How many requests per session? Convert to average QPS. DAU times request divided by sessions divided by 86,400. Convert to peak. Average times 10. Step 2. Identify the resources. HTTP layer, database connections, database read throughput, write throughput, storage for row, storage for binary files. Step 3. Find the binding constraint. Which resource hits its ceiling first? At small scale, almost always connections without pooling or missing indexes causing slow queries. At medium scale, read throughput or connection pool saturation. At large scale, write throughput or storage. Step 4. Fix with minimum change. Missing index is free. Connection pooling is a configuration change. Vertical scaling is a plan upgrade. Read replica is a new infrastructure plus routing logic. Sharding is an architectural change. The cost of each fix scales with the rungs of the scaling ladder. Start at rung 1. Failure mode estimation. 4 failure modes to estimate before they occur. Connection exhaustion at around 100 concurrent requests without pooling. Silent until checkout starts failing. Symptoms are 2-minute connection errors and P99 latency spikes. The prevention, PG bouncer via Supabase pooler. This is already in place. Slow queries as tables grow past 100K rows. Without proper indexes, run nonlinear query time growth. Symptom is slow, P99 with no clear error. The prevention, run, explain, analyze on any query over 100 milliseconds. Index every foreign key and common filter column. Stripe rate limiting at 100 checkout requests per second. The checkouts fail with a 429 from Stripe. Not a concern at my scale, but prevention at scale. Queue checkout calls with exponential backoff. Memory pressure when working set exceeds shared buffers. Cache hit rate drops. Query latency increases gradually with no hard failure. The prevention, monitor shared buffers hit rate. Vertical scale when it drops below 85% consistently. Find the binding constraint. Fix it cheaply. Estimation goal, find which resource hits its ceiling first, not predict the exact number. At 1,000 DAU, the binding constraint is connection management. At 1 million DAU, it's read throughput. Fix the actual constraint. The numbers to know, 86,400 seconds per day, around 10,000 Postgres reads per second, 100 default max connections, around 1 millisecond SSD read, around 100 milliseconds cross-region latency, around 200 milliseconds Stripe API call. These let you do the envelope math in 60 seconds. Row storage is cheap. Binary files are what drive storage costs. Order tables at 5 years of 1,000 per month is 60 megabytes. Product images at 100 products times 3 variants times 500 kilobytes is 150 megabytes. Store files in Supabase storage. Latency budget. Stripe dominates checkout at 77% of the budget. DB operations are fast. The 2-second SLO has an 87% headroom. Async operations are in the outbox. They don't block checkout. Okay. Failure modes in order. Connection exhaustion first. Slow queries from missing indexes second. Memory pressure from working set exceeding cache third. All have cheap preventions before they become problems. For a client, capacity planning for this platform is documented with current utilization, ceiling values, and headroom for every resource. The binding constraint at current scale is connection management. PG bouncer is in place. The checkout latency budget is documented with each operation contribution. Failure modes and their trigger points are identified and mitigated proactively. Unfleshed out thoughts. I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. If you're working through capacity planning for your own platform, latency budgets, QPS estimation, or failure mode analysis, reach out. I'm open for freelance projects and consulting. The full post is linked in the description below. Capacity worksheet, latency budget template, and failure mode reference. Next in this series, front-end architecture, the component pyramid, server components, and data flow. I'll see you there.